This is the second part of the presentation on the topic of network models. In this video, I'm going to talk about maximum flow problems. Just like the first video, this presentation corresponds to the material on your textbook, Wayne Winston's textbook, Chapter 8. In the previous topic of network models, we have seen another problem, which is the shortest path problem. Now here we are going to look at another problem, which is called maximum flow problem, which can be modeled also as a network, such that it can be solved more efficiently. Now, what's the difference? The difference is that in the shortest path problem, we have distance value that corresponds to every single arc in the network. So from, let's say, node 1 to node 2, we have the distance of 3 kilometers or something. Here, the difference is that each arc has a capacity. So it's not about the distance, it's about the capacity. How much or how many quantity that can flow through an arc that you can ship, you can send through that arc. So each arc has a capacity. So the problem is to have a starting point, the source of, you can think about the source of water, the source of oil, the source of cars getting into the city, the source of items or goods that's flowing out from a factory. And then we have also a terminal point, which is called a sink. Sink is the place where all these flows will gather together into this point. So source is the place where the flows going out. The sink is the point where all of those flows going in. In maximum flow problem, we need to transport the maximum amount of flow from source to sink. So we have a network of arcs, we have a lot of nodes. Each arc may have different capacities. Our goal is to try to transport as many amount of items that we have, as many of those items as possible from the source to the sink. So that's our problem. Notice that it's very different with the shortest path problem, where in the shortest path problem, we want to go from one point to the other point with the shortest distance as possible. Here we want to maximize the flow that we can push through the network or flowing through the network from the source to the sink. You might wonder why I really wanted to emphasize the difference between this problem and the shortest path problem. Well, because first in the exam, I guess the problem will not tell you whether this is shortest path or maximum flow, so you have to decide correctly. And second, in the real world, when you are being a consultant or something, you need to model the problem and you have a correct idea about either modeling this problem as a shortest path problem, or is this problem actually a maximum flow problem? So you really need to be able to differentiate these two problems so you know that, okay, if I have this problem, it falls to this category. If I have that kind of problem, it falls into the other. Now let's see an example of Sunco oil. It says that we want to ship the maximum possible amount of oil from node source to sink in figure 6. So we are given the source, we need to transport the oil all the way to the sink. However, we have some stations 1, 2, and 3 that we need to pass our oil through. And these pipes of between 1, 2, 3, and the other nodes, they have different diameters. So the value here is the diameter of a pipe. So from source to 1, the diameter is, let's say, 2 meters, but from 1 to 3, you have a bigger pipe with the diameter of 4 meters. And then, so those number is called arc capacity. Let's say in this pipe, you can flow oil through from source to one, something like, let's say 2 liters every second, something like that. So it corresponds with the diameter. The bigger the diameter of the pipe is, the more flow you can flow through, the more oil you can flow through that arc. Okay, and then so this table simply shows the capacity that you can flow through an arc, and then maximum flow problems want us to determine how much oil we need to flow through every single arc in this network, such that the oil that we receive at the sink is maximized. We are not going to solve that example yet, but we're going to talk about some characteristics of this problem. So the node source is called that way because things flow out from it, but nothing goes into it. Okay, so you see from the source, the oil flows out. For this moment, try to ignore this artificial thing for a while. So other than this artificial thing, everything flows out of source, nothing goes into it. For node sink or SI, everything flows into it, nothing goes out of it. Again, for the time being, ignore this artificial arc, okay? So if you ignore this A0 in the bottom, you can see that everything just flows into the sink. Nothing flows out from the sink. Now, another thing is that for the flow to be feasible, for your solution to be feasible, your solution or the flow must have these characteristics. The first one that the constraint says that the flow through each arc must be between 0 and the arc capacity, which is obvious because let's say the capacity is 4 between node 1 and node 3. Of course that the oil that goes through this arc must be between 0 and 4 at most. Cannot be negative because you just cannot flow negative amount of oil. It doesn't make sense, right? And then you cannot also exceed the capacity of the pipe. If the pipe can only flows 4 liters of oil every second, let's say, then you just can put the oil as much as that every second through that pipe. Okay, so this constraint makes sense. The flow through each arc must be between 0 and the arc capacity. Now, the other thing that makes a solution feasible for this problem is that the flow into node I, so any node in your network, must be the same with the flow out of that node, which again makes sense. For example, imagine if you put some oil from 1 to 2 to flow through this arc from 1 to 2. Of course, those oil cannot stay in node 2. They must flow out of node 2. So this constraint says that to make a feasible solution, anything that goes into a node must go out from that node at the same amount, because we're talking about flow, right? If you have something flowing like oil, water, or something, if it reaches a node with that amount, let's say 2 liters reaching a particular node, then that node must flows that 2 liters out of that node until it reaches the sink. Now it's time to talk about this artificial arc. So because of this constraint, the flow conservation constraint, what goes in must go out. So for source and sink, they actually, we know that source actually only have things that flow out from it, nothing goes in. But to make a solution feasible, we need to say that there is an artificial arc. So artificial is something not real, is something dummy that we say is flowing from sink to source. Once we have this artificial arc, we can say that every single node in our network satisfies this constraint. Anything goes into it will flow out of it. Now you can see with the artificial arc that we have, everything that flows into the sink will go out. And anything that goes into the source will flow out. Of course, this is just an artificial arc, so it is not there physically or in reality. It just helps us later to formulate a solution for this problem. Talking about the solution for this problem, let's see an example of a feasible solution for this kind of problem. So the values inside the parentheses, these values shows your decision to flow how much oil through that arc. And the value outside of the parentheses, so this value outside of the parentheses, they show the capacity of the arc. So let's see what does this feasible solution says. So it says that from source to the first node, we assign the flow of 2 liters of oil, something like that. And then those 2 liters of oil will go through from 1 to 2. All of them, 2 liters go from 1 to 2. And then again, those all 2 liters will go from 2 to the sink. And then to make this solution balance, we have an artificial arc that say those 2 liters flows back from the sink to the source. And then because these numbers are 0, let's say from 1 to 3, you see the number here is 0. It means that nothing flows through 1 to 3. Also, nothing flows from 3 to sink. This is not an optimal solution. This is just a feasible solution, which means that this is an okay solution, acceptable, reasonable. We are not talking about optimal solution yet. Okay, so this is again just a feasible solution and how to read the network. And then you can also use this notation to say the x variable from source to 1 equals 2. The x variable x13 is 0 because nothing flows from 1 to 3. X3 sink is also 0 because nothing flows from 3 to sink, and so on. Now let's revisit a bit about the artificial arc. So we need to have an artificial arc A0 because it would allow us to write the flow of conservation of flow constraint for source and sink. This conservation of flow constraints is the one that says anything goes into a node must be exactly the same with anything goes out from that node. Okay, without this artificial sink, we cannot say, we cannot define that constraint for source and sink. Now, if we say that x0 is the flow through artificial arc. So here in the previous example, x0 equals 2. So if we say x0 is the flow through the artificial arc, then our goal actually is to maximize x0. Okay, remember that maximum flow problem wants us to maximize the flow that we can push through from source to sink. Now the artificial arc goes back from sink to source. So we can say that, okay, we can try to maximize x0, which is equal to maximize the things that we can push through from source to sink through the network. Okay, so here we can also say our goal is to maximize x0. Because if you think about it, x0 is all the amount that the sink receives. In the previous slide, we have the feasible solution for the problem. And then here we have the optimal solution for the problem. So here, if you look at these variables, each of this shows the value that how much oil flows through every single arc in the network. And then if you look at the x0 equals 3, you instantly know that the maximum value of oil that can flow through this kind of network is 3. I'm not going to talk about how we can get this optimal solution yet, but this is just about how to read an optimal solution, especially reading this x0 equals 3 part. So this is the amount of the maximum number, the maximum amount of oil that we can flow through from source to sink. Maximum flow problem doesn't always have to be about flowing liquids through a network of pipes. It can be about we are trying to have as many planes as possible flying out from a city to another. So that's what this example shows. So we have two cities. The source is the city called Juneau in Alaska, and another city is called Dallas in Texas. And then we cannot have a direct flight through the cities, so we have to have a stopover in the other cities, Seattle, Denver, and Los Angeles. However, because of the limited landing space, the number of flights between pairs of cities is limited, as shown in Table 9, or is also shown as the number here, above each arc. So let's say from Juneau to Seattle, you can only fly 3 planes daily. Now this problem wants us to give the solution about how to maximize the number of connecting flights daily that can fly from Juneau to Dallas. The maximum problem can also be used to maximize the number of couples that we can match together. So here in this example, for example, you have 5 male celebrities. So these people are from the 90s and 80s. So probably you need to Google them to look at who they are and how they look like. Actually, how they look like, I will show them how they look like in the next slide, actually. And then you also have 5 female celebrities. And then you try to pair them up for to maximize the number of pairs at a dance party. However, it will be easy if everybody is compatible with the other. Compatible means you are friendly, you're okay to have a dance with that person. In this problem, however, there are some people who are compatible only with some others, but then they're not compatible with the other person. So by not compatible means that you cannot match them up. They'll have a fight or something. I don't know. So looking at this compatibility, you need to provide a solution to maximize the number of pairs that are compatible for the dance. You might think that what is the connection between compatibility and maximum flow problem? remember in maximum flow problem, each arc shows the capacity. What is the capacity of an arc has anything to do with compatibility? Well, we can model those compatibility as the capacity of an arc. For example, like let's say in the previous example, let's see Michael Jackson MJ. He's only compatible with LA, Laurie Anderson, I think, and then with Meryl Streep, and then with Victoria Principal. So from MJ, Michael Jackson, you only draw these arcs with capacity exactly 1 with the other female celebrities whom he is compatible with. Or he was, I said. And then what about from source to sink? Well, from the source, you can just model that everybody gets one. You can imagine that everybody gets one dance ticket, something like that. And then that ticket can be matched with the other female celebrity. And then from each female celebrity, you can draw an arc going through the sink, which with again capacity 1, which means that each female celebrity at most can receive 1 ticket for going to dance. So the male celebrity has 1 ticket, and he can give that 1 ticket to the female whom he is compatible with. And then from the female artist to the sink, the capacity is 1 again, which means that she can receive at most 1 ticket. So this is how we can model that problem about who is compatible with whom, and then maximize the number of compatible pairs. And then apparently the maximum flow for that kind of numbers is 4. So unfortunately, we cannot match 5 of these male performers with 5 of these female celebrities. And then this is the result of the maximum flow. So somebody's not going to the dance. Let me check who's that. Kevin Costner is going, Burt Reynolds, Michael Jackson, Tom Cruise. So Tom Selleck is not going. And then on the female side, who is not going? Laurie Anderson is going, Meryl Streep is going, and then Katharine Hepburn is going, and then Victoria Principal is going. So finally, LE is not going. I must honestly admit that I forgot who she is. I'm so sorry. I think I'm going to make the next part of this video about maximum flow problems. Otherwise, the video will be too long, like 55 or even more than an hour. And I think you would prefer some shorter videos. So see you in the next videos about ford-fulkerson method, which is the method that we can use to find the optimal solution of the maximum flow problems. Thank you.